This is lab 4, Faraday's law. The purpose of this lab is to collect observational data of a magnet flowing through a conductive tube of aluminum foil. We're going to model the magnet and tube computationally and compare the computational predictions to the observed data. The principles that we are going to use is Faraday's law. It's a magnetic flux that changes in time that creates a non-Coulomb electric field that generates voltage. Magnetic flux, which measures the total magnetic field. Lenz's law, the current opposes the change induced on it. Ohm's law, which is electric resistance. And Newton's third law, the opposite forces are equal. You can see Faraday's law and Ohm's law given here. So in the experiment, what we do is we have an aluminum tube, and we drop a magnet with the north end facing down the tube, and then we record the time it takes for the magnet to reach the end of the tube. The system is the magnet, and the surroundings is the tube and everything else. And the initial condition is the magnet above the tube. And we assume that only gravity and magnetic forces are acting upon the magnet in the tube. So when we took the time, so when I manually got the data, I got the trials of 0.61 seconds, 0.63 seconds, 0.62 seconds, 0.65 seconds, and 0.62 seconds for an average time of 0.626 seconds. The tube length was 0.35 meters long. The tube width, the actual width of the aluminum, was 0.005 meters, and the inner radius of the tube 0.0125 meters. The magnetic mass had a weight of 0.025 kilograms, and the magnetic dipole was 3.29 amp meters squared. So when we simulated the tube, you can find all of the information of how we simulated it in the glow script model included in the link below. But we got around 0.8 seconds. Some of the errors that we might be able to think about is the fact that there was some friction in the tube that we might have not accounted for, and maybe there was some air resistance as well, or maybe there were some errors in timing or some errors in timing as well. We don't know if there might have been any indications with the tube itself, some imperfections. That's also something that we could potentially consider in terms of errors. So some what-if questions. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So first, this would cause a larger induced current, which would lead to a larger magnetic force, which means that there'd be more interactions between the magnet and the conductive tube. So it would take longer for the magnet to go through the tube. And if holes or slots were cut into the tube, what would happen is the magnet would actually go faster because the induced current decreases. There are less interactions between the magnet as it's falling down the tube and then the tube itself. This is the slab. Please view the code in the description below to see all the information about the code. Thank you very much.